Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today my group will be present for the electrical machine project. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So before we start the group presentation, so let me introduce my group member. So we have Muhammad Nafis bin Muhammad Nazri, we have Ahmad Daniel bin Awang, we have Muhammad Hafiz Zaki bin Yunus, we have Ikmal Hakim bin Muhammad Hafiz Robert, and lastly we have Ikhwan Al-Mu'min bin Japri as the group leader. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ikhwan Al-Mu'min bin Japri and my number is CE240156. So for the introduction part, so through the project that we have done for this group project, so we face a few challenges where we notice a power loss of 0.8 volt due to the internal wiring resistance, and then we also noticed that the metal brushes sometimes did not make a stable contact, so causing a small spark and uneven rotation. And then the speed was not consistent, likely because the copper coil were handmade, so it was not perfectly aligned and some part create a friction. So the motor top speed was also limited as the back EMF 11.199 volt was very close to our 12 volt supply. So we just using a simple material like a cardboard and aluminium to keep the cost low, and also they also introduce a mechanical limitation that make the motor less smooth. So I will continue for the design planning and also for the design process. So for the design planning, so this DC motor is actually to demonstrate, is built to actually demonstrate how electromagnetic force can create a motion lah. So we keep the design and the cost effective by using everyday material like copper, wire, magnet, paper clip and a cardboard lah. So the planning process involves selecting suitable components, sketching a basic layout and dividing the work into the key stage. So special attention also was given to the commutator and brush setup to ensure smooth and continuous rotation. So for the design process, so the brush DC motor is built to show how the electric current and a magnetic field can create a motion and also can generate a voltage lah. So we just using a wooden dowel serve as the rotor shaft with a small wood piece and L-shaped iron bracket as a coil support lah. So the copper wire was wound into becoming a coil for like 50 turns like that, and then at the end of the coil were shaped into a basic commutator where the aluminum will act as a brush to transfer the current to the coil to the end of the coil. So when we place two magnet on each side, so when the DC motor is applied to the coil, so it can generate a magnetic field that interact with the magnet causing the rotor to spin continuously. So that's all from me. Thank you.
We use multisim to model a DC motor and study its electrical and mechanical performance. Armature resistance and inductance were measured with a resistor and inductor connected to a DC source, while a current sensor tracked motor current in real time. On the mechanical side, the motor shaft was connected to a simulated load and motion sensor to measure speed. To test real-world conditions, we added a torque load and used converter to display speed and current live. The simulation ran in continuous time, helping us to observe how the motor reacts to changes in load and voltage. Our motor project combined core electrical engineering principle with hands-on design. The main concept is simple. When current flows through a wire in a magnetic field, it creates motion. We focus on making the motor efficient and cost-effective, using materials like copper wire and basic magnets. Simulations help us test the design before building, and the final motor reached up to 4006 RPM, very close to our predictions, with about 93% efficiency. Along the way, we learned the importance of careful testing and adjusting things like wire connections and alignment. Overall, it was a great experience turning theory into a working machine.
So, hi, my name is Muhammad Hafiz bin Muhammad Nazri. My meeting number is AE230034. So, today I'm going to present about the list of material that we use. So, the first one is battery 12 VDC. The quantity is 1. Second is copper. Description is the rotor winding. And the quantity is 50 turns. Third is neodymium black epoxy magnet. As a permanent magnet, the quantity is 8. The fourth is iron elbow as a stator, and the quantity is 2. Number 5 is aluminium wire as a carbon brush, is 20 cm. And then is cardboard paper as a base, and the quantity is 1. And lastly is wooden stick as a rotor shaft, and the quantity is 1. Okay, next I'm going to present about the description of assembly work. The first one is rotor shaft, wooden dual drill at both end, mount on iron L bracket for stable rotation, and then coil support, coil placed on a cardboard base for insulation and lightweight structure, and for the coil winding, 50 turns of magnet wire on each side and sweep to act as a commutator. And then the commutator, wire ends tape at 20 to 30 degrees angle on the shaft for proper current timing. Next is rotor stand. L-shaped aluminum wire held the shaft in place and allowed smooth spinning. Then brushes, copper wire position to maintain contact with commutator ends. Next is magnet. Two magnets align with coil to provide a stable magnetic field. And then lastly is testing. When voltage applied, rotors spin continuously due to time switching and magnetic force.
Assalamualaikum and hi everyone. My name is Ahmadin Mila Awang and my metric number is CE240100. I will talk about the experiment setup. So for the DC motor circuit was designed and simulated using multisim to observe its electrical performance. A 12-volt DC power supply was connected to the motor. Key parameters such as voltage, current, and angular speed measuring using a multimeter and a oscilloscope. This setup allows for real-time monitoring of the motor behavior. For the measurement and troubleshooting works, during the simulation, the EMF at the motor, which is EA terminal, was recorded at approximately 11.199 volt with a current draw of 1.001 ampere. The supply voltage remained constant at 12 volt. Angular speed was observed using the oscilloscope, which display ramp up waveform indicating 1 pulse per revolution of the motor. Troubleshooting steps include verifying the motor connection polarity, measuring correct measurement tool setting, and checking the signal conversion. The block to obtain angular speed in degrees. For the comparative study, based on simulation, we got EMF is 11.199 volt. After that, we can determine the efficiency, which is using ratio of back EMF to the input voltage, and we get the efficiency is 93.33%. This shows the motor has better efficiency. From the oscilloscope, we can determine the RPM. The reading pulse is 14.977 millisecond. From that reading, we can find the frequency and assumption of 1 pulse per revolution. After that, we can find RPM, multiplying with 60 seconds to get RPM and get the 4006 RPM.
Assalamualaikum and hi everyone. In this demonstration, we will show you how our prototype DC motor operates. So first, connect the motor to a DC power supply. In this setup, the supply is 12 volt DC to the motor terminals. The motor runs at its maximum speed because there's minimal mechanical resistance. The only torque required is to overcome internal friction and windage losses. As the voltage increases, the speed increases proportionally under no load because there is no opposing torque from a load. That's all for the demonstration. Thank you.
So for the discussion part, the project successfully demonstrated how a simple brush DC motor converts electrical energy into mechanical motion using basic materials like copper wire, magnets, cardboard, and wood. The motor spin smoothly under a 12-volt supply, meeting the project's objective. Simulation results show a back EMF of 11.199 volt and current of 1.001 ampere, indicating a small internal voltage drop. The motor achieved an efficiency of 93.33% and a speed of 4006 RPM, confirmed by oscilloscope waveform. Troubleshooting steps such as checking polarity and calibrating measurement tools were essential to ensure accuracy. This highlights the importance of detailed testing in engineering work. And for the conclusion, overall, the project successfully met its objective by building and simulating a working brush DC motor using simple low-cost materials. The motor's high efficiency and stable performance align well with electromagnetic theory and practical expectations. Throughout the project, we gain hands-on experience in motor design, simulating using multisim and performance analysis. It also strengthened key engineering skills such as system integration, problem solving, and teamwork. For future improvement, the motor design could be enhanced with optimized coitance, stronger magnets, or upgraded components for better performance.